If we look inside of atoms, we see that they have two major segments to them. The nucleus, which has protons and neutrons in it, and an electron cloud, which has the electrons in it. In addition to being referred to as a cloud, this can sometimes be referred to as shells, valences, or orbits. So if any of those terms seem familiar, they are all essentially equivalent. And the reason there's so many names here is that, in the last 150 to 200 years, as we've been developing our understanding of atomic structure, they've had different theories about what things were like in there. And until recently, when we had the technology to really view the inside of atoms, they had to make some guesses. So they explained it using concepts they already understood. We know now that electrons are far more unpredictable than they are predictable. And so none of these terms are really ideal. Cloud is the best because it's kind of undefinable. When we talk about these particles that are inside of atoms, we talk about their charge and we talk about their mass. Their charge is a lot like how you would discuss the charge of a magnet. They're either positive or negative, and in some cases they're neutral. There is no charge. So protons are positive, neutrons are neutral, and electrons are negative. In terms of mass, we talk about their mass in atomic mass units, or AMUs. And this is a measurement of convenience. I don't know if you've ever thought about how exactly measurements become measurements. So how did a meter become a meter? How did a foot become a foot? How did a cup become a cup? Well, somebody decided that the cup in Aunt Joe's cupboard was going to be the cup that everybody was going to use to measure things from this day forward. And everybody else kind of said, okay, let's go with that. So in the case of the atomic physicists, they said, well, we have decided that one atomic mass unit is going to be the mass of one proton. And that's very convenient because then when you're doing your measurements, you just say, well, a proton weighs 1. Turns out that neutrons had almost identical mass, and so that's also very convenient. And electrons are very, very small by comparison. They're about 1/2000th of an AMU. Now this is so small that it's almost not worth counting. And so a lot of times when we talk about electrons, we talk about them basically having no mass. They do actually have a mass, but it's so small it's not worth counting. So I kind of think about it, like when I'm baking a batch of cookies. And somebody says, well, how many cups of dough do you have? Well, I had a cup of flour and a cup of sugar and a cup of butter and a cup of chocolate chips. So I have 4 cups of dough. But what about the pinch of salt I put in and, the couple drips of vanilla? Well, they're in there, but they're so small they're not worth counting because I'm thinking in large scale. And AMUs are large scale units by comparison. Do electrons have mass? Yes. Is it worth counting when we're talking about total mass? No. If you look into a typical atom of a typical element, it's not really about being normal. There really is no such thing as normal. But most atoms that we talk about are neutral. And neutral atoms have equal numbers of protons and electrons, no net charge, and their mass would be all the things that are worth counting. So it would be the protons plus the... You might then ask, well, how do I know how many protons and electrons we have in here? And that's a really good question. It turns out that all of the atoms of an element have one thing in common, and that is the number of protons. So the number of protons really define the element, define the atom. All the atoms of that element will have the same number of protons. And it's very difficult to change that. It can be done. We have recently developed the technology to change the number of protons, but it is not something that occurs naturally. The number of protons in an element is typically very stable. And so we have developed a term or a concept called the atomic number that is the number of protons. And if it's neutral, that also is going to tell me the number of electrons. So for example, if I told you that carbon is number 6, and if you look on the periodic table, very often the number is written above the symbol, then you could very quickly tell me that, well, if this is neutral, the protons is 6 and the electrons is 6. If we were looking at sodium, which is number 11, then the protons is 11 and the electrons is 11, assuming these are neutral. And if we were looking at calcium, number 20, protons is 20, electrons is 20. In general, unless it's stated otherwise, you could assume that an atom is neutral. The only part of this that we don't have yet then is the number of neutrons in each of these. And to know that, we'd have to either be told or we'd have to know the mass. So in this case, I'm going to tell you the mass. The mass of carbon is 12. If mass equals protons plus neutrons, then 12 is 6 plus whatever the neutrons is. Do a little quick math rearrangement, and that means my neutrons is 6 for carbon. Sodium, mass is 23. Mass is protons plus neutrons, so 23 equals 11 plus some number of neutrons. Do a little math. I should get that there are 12 neutrons in sodium. Calcium, mass is 40. Protons is 20. And so 40 is 20 plus some number of neutrons. 20 should be my neutrons. All the questions on this exam about these kind of topics are multiple choice, so the answer should be there in front of you. It's not like you have to do this math on the paper and show your work. You just need to be able to use these concepts to determine if you're given an atom with a certain atomic number and certain mass, can you tell me how many protons, neutrons, and electrons it should have? So some atoms, in order to become more stable, will gain or lose electrons. And so being neutral and being stable aren't exactly the same things because there's internal energy interactions going on inside of an atom between the protons and the neutrons and the electrons. And if you want more about that, I would highly recommend you go take chemistry. But this is just part of the reality of the natural world, that being neutral and being stable are not always the same thing. So when an atom needs to be more stable, it can take electrons or it can give away electrons. But when it does that, it's going to influence its charge. If it becomes positively charged, we refer to it as a cation. And if it becomes negatively charged, we refer to it as an anion. Those words might sound familiar. They're like the cathode and the anode of a battery. The cathode's the positive end, the anode's the negative end. We also used a similar set of sound-alike words in the previous lecture where we talked about catabolism and anabolism. And I hate sound-alike words, just the death of me. So what occurred to me one time is that T is kind of like a plus symbol, and that's how I remember that cations are the positive ones and anions are the negative ones. The other kind of unusual atom that we sometimes encounter is called an isotope. And isotopes are just naturally occurring atoms that have more or fewer neutrons than other atoms of that element. Carbon, for example, has an unusual form that has 8 neutrons instead of 6, and so it weighs 14 atomic mass units instead of 12 atomic mass units. We use that because we've determined that carbon-14 that naturally occurs slowly decays over time, loses those neutrons, and becomes carbon-12. So if you take something very old and compare the amount of carbon-14 it has in it to the amount of carbon-12 that it has in it, you can estimate its age. We also use this in medical tools. For For example, we'll put iodine isotopes in people to see whether or not their thyroid is effectively picking up iodine and using it to make hormones. We can use it as radioactive dyes to highlight certain area of the bodies and their function or their flow. So this is actually a really useful tool for medical studies and for science to be able to have these different variations on atoms that exist.